In this video, I'll be going over some of the other common types of equations that we see in pre-calculus. The first is to go through the types of equations that have rational exponents. So a rational exponent is any exponent that is a fraction. Now, what a rational exponent is telling us, so if I have 8 to the 2/3, the 2, or the numerator here, is telling us what power we're raising the 8 to. And then the 3 is telling us what root we're taking of 8. So we can think of 8 to the 2/3 as 8 squared cube rooted, or we can think of it as the cube root of 8 all getting squared. It doesn't matter which order we do those in. So if I do it 8 squared and then cube rooted, so 8 squared is 64. Cube root of 64 is 4. Or I could do cube root of 8 is 2. Then that getting squared is 4. So either way gets us to the solution. All right, and then 64 to the negative 1/3. Remember, if we have a negative exponent, that's the same thing as putting that base raised to the positive of that exponent. So this is 1 over 64 to the 1/3. 64 to the 1/3, that just means the cube root of 64 and then raised to the first power. Well, the cube root of 64, we already saw that over here. So cube root of 64 is just 4, so this is 1 over 4. Okay, so that's how we evaluate a base number that is getting raised to a rational exponent. So what do we do when we have an exponent, or I'm sorry, an equation that has one of these rational exponents? Well, if we remember, if we back up, suppose I had x to the squared, x squared equals, 49. What we do is to undo that squared power, we'd square root both sides. Another way to think of this is I could rewrite that radical symbol. I could write it as a 1/2 power. So x squared to the 1/2. By doing that, the 2 here and the 1/2, when I multiply those exponents, I get x to the first power. So x to the first is equal to 49 to the 1/2 power, which just means the square root of 49. So plus or minus 7 here. Okay, so all that to say, if we multiply by the reciprocal of the power, that undoes that power. So I'm going to multiply or raise both sides to the 4/5 power. That means on the right side of this equation, those are going to cancel. I'm left with x. 32 to the 4/5, so that means the 5th root of 32 raised to the 4th power. The 5th root of 32 is 2. Then I'm going to raise that to the 4th, so this is 16. So x is going to be equal to 16 here. The second one, we have y to the 3/2 power equals 125. Again, I'm going to raise this to the 2/3 power, so I'm going to raise that to the reciprocal. On the left-hand side, those exponents multiply out to 1, so I get y to the first is equal to cube root of 125 squared. Oh, similarly, I could have done 125 squared, squared, and then cube rooted. The problem with this is that 125 squared is going to be a really big number, and I can't do that in my head. Similarly, that really big number, I don't know what the cube root of that is. So by taking the cube root first, I end up with smaller values that are easier to work with. So the cube root of 125 is 5, and then we square that, so 25 is what y is equal to here. Moving on to the next type of equation, which are radical equations. These are all examples of radical equations. These are just equations that have a radical term, so something that is getting square rooted. This is an important point that I want to mention. When solving an equation by squaring both sides of the equal sign, it is vital to check all solutions. It is possible to end up with extraneous solutions. That just means extra solutions that don't actually solve the equation. So we'll make sure that we check all of these. So in this first example, I'm going to square both sides. Squaring a square root gives us just the radicand left over. Now this looks like a quadratic equation that I'm going to set equal to 0 and bring all the terms to the same side. And then this factors x plus 5, x minus 3. Setting those equal to 0, I get x is equal to negative 5, x is equal to 3. And then we just have to check both of those to make sure that these actually solve the equation. So what I'm going to do, wherever x is, first I'm going to put this negative 5. So 15 minus 2 times negative 5. Negative 2 times negative 5 is positive 10. 15 plus 10 is 25, so square root of 25 is 5. So on the left-hand side of the equation, I get 5. And I want to know if that is equal to the right side. Well, when I plug in negative 5 on the right, that doesn't equal 5. So negative 5 is not a solution here. When I substitute in 3, let's do it in a different color. So when I substitute 3 in for x, I get 15 minus 2 times 3. Minus 2 times 3 is negative 6. 15 minus 6 is 9. So I get the square root of 9. Is that equal to 3? And those are equal. So my one and only solution is x equals 3 here. Okay, let's do the next one. Here I'm going to square both sides. So it's a little more complicated just because when I square the right-hand side, that is a binomial that I need to expand. So x plus 3 is equal to, on the right-hand side, I'm going to get 9x squared minus 3x, so minus 6x plus 1. Moving everything to the right, I'm going to get 9x squared minus 7x minus 2. And then here, I'm going to need to try to factor this. Let me think about whether this can be factored. It can be factored. I know the only factors that are going to multiply to negative 2 are 2 and 1. And then this might require a little guess and check. I'm going to try 3x on both sides. So 3x minus 6. I don't think that's going to do it. I think I want to do x and 9x. 9x squared. That's going to give me the solution, or the correct factorization. And remember, you can always check by multiplying this out. I get 9x squared. The inside and the outside, I get negative 9x and positive 2x. Negative 9x, positive 2x gives me that negative 7x in the middle. And then I have negative 2 from negative 1 times 2. So that's all good. Setting these equal to 0, I get x equals 1, and then x equals negative 2/9. When I substitute in 1 here, let's see what we get. I get, on the left side, I get 1 plus 3 is 4, square root of 4. On the left, when I substitute in 1, I get 3 times 1 minus 1, I get 3 minus 1. 2 is equal to 2, so that works. So x is equal to 1. And then when I substitute in negative 2/9, this one's not going to be quite as quick. So negative 2/9 plus 3, well, 3 is 27/9, 25/9 on the left-hand side. Is that equal to negative 6/9 minus 1? Well, I don't even need to go any further because on the right-hand side of this equation, I'm going to get a negative. On the right-hand side, I get a positive, so that's not going to work. But this is 5/3. And on the right-hand side, I get negative 15/9, which is negative 5/3. So that is not equal. So my one and only solution is x is equal to 1 here. Visually, let me just say one more thing about this equation. Visually, if I graph the left-hand side and the right-hand side of this equation, x plus 3 square rooted is just the square root, the graph of the square root function shifted left 3 units. So that is square root x plus 3. If I graph 3x minus 1, well, that is a line with a slope of 3 and y-intercept of -1. So if I look at these graphs, there's only one position where these intersect, and that's at +1. So that's another way we can verify that there's only one solution. There's only one place that these two graphs intersect. All right, next up, absolute value equations. So to solve an absolute value equation, we notice that the absolute value will be equal to 8 for this one. What we need to say is that, well, for this 2x minus 6, the absolute value of that, for that to equal 8, the inside value must be 8 or -8. So what we do is we split this into two equations, one where it's equal to 8 and one where the left side is equal to -8, and then we just solve those. Okay, and the reason is because if I take the absolute value of something like this, whoa, there's a truck outside. If I take the absolute value of this, absolute value of x is equal to 5, there are two values that x could be. It could be -5 or it could be +5. So that's why we split this into two equations, where one equation is the original positive value and the other equation is the negative. All right, so what we want to do is we want to take what's inside the absolute value and set it equal to 8 here and then -8. And then I just solve these linear equations. 6x is equal to 4, x is equal to 4/6, which is 2/3. And then on the next one, 6x is equal to -12, x is equal to -2. So those are the two solutions. I'll go in order of the letters here. On part B, well, here I have 3x plus 4 is equal to -9. An absolute value expression can never equal something that's negative. So here we're going to say no solution. Graphically, an absolute value equation is, it looks like a V. So I don't know precisely what this looks like, but it's a V and it's shifting up 4 units. So it's going to look something like that. And then -9 is way down here. So here's the other part of that graph. So as we can see, those never intersect. So this is a way we can visually see that there's no solution. All right, on part C, what we want to do first is isolate the absolute value. And then, so we set 3x minus 5 absolute value equal to 10. Now split it into two equations. And then we just solve down. So x is equal to 5. X is equal to -5/3. Visually, if we were to graph this, I want to see this thing right here. 3x minus 5, when is that equal to 10? So 3x minus 5, I know that's going to be down 5 over here. And then it's going to hit 10 right here, so I can see those are going to be the two solutions. So 5 and -5/3. Not precise, but that's the idea. That V-shaped graph hits the line 10 at two spots. All right, and then this last one, -5x plus 10 absolute valued is equal to 0. So I don't split this into two equations because I can't take the positive or negative of 0. So I just set it equal to 0. 10 is going to be 5x here. X will be 2. And graphically, what this is saying is, well, this is going to hit 0. I don't know exactly what this graph looks like, but let me think about this. When x is 0, I get 10. When x is 1, I get 5. So this graph looks something like this. And what we can see is it hits 0 at only one position. All right, and then lastly, we want to look at equations that look like quadratics, but they're not actually quadratic equations. So there's a couple ways we can do this. This first example, x to the fourth, and there's a small typo. This should be 17x squared plus 16. So a couple ways we can do this. One way is to do a substitution. So I'm going to say let y equal x squared, and then y squared is equal to x to the fourth. And so I rewrite this equation. And let me back up. The reason that this looks like a quadratic, but it's not really, is because quadratic equations always have the highest exponent as being squared. But here, the highest exponent is raised to the fourth. But we can treat this as a quadratic because that highest exponent is doubled this this second exponent. So I can do this substitution. So what we'll do is, in place of x to the fourth, we're going to write y squared minus 17y plus 16 is equal to 0. And what we can see is now this is a quadratic equation. We can actually solve this quadratic equation by factoring. So y is equal to 16, y is equal to 1. But I don't want to solve for y. I ultimately want to solve for x. So what we saw is that y is going to be x squared here. So x will be plus or minus 4, and then x squared is equal to 1. X will be plus or minus 1. So I have 4 solutions, and that makes sense because the original equation was raised to the fourth power. All right, a second way we can do that, so that's the first way, is by making a substitution. The second way is just factoring this right off the bat. Okay, so two things that multiply to x to the fourth are x squared and x squared. Okay, and then multiplying, two things that multiply to 16 that add to negative 17 are negative 16 and negative 1. So I get x squared is equal to 1, x is equal to plus or minus 1, and then x squared is equal to 16, x is equal to plus or minus 4. So that's how we get those 4 solutions. Okay, and then another one that's quadratic in form is this one down here, x plus 2 squared plus 11 times x plus 2 minus 12. So we can see is this thing, x plus 2 is getting squared, and then I have it right down here. So again, I'm going to make a substitution. I'm going to say y is equal to x plus 2. Okay, so by doing that, I get y squared plus 11y minus 12. Now this one's quite easy to factor. This is just going to be y plus 12, y minus 1. Okay, and then what we can do is we can set those equal to 0. Y plus 12, so let's say y is equal to negative 12, y is equal to 1. But now I'm going to substitute in that x plus 2 for y, because I ultimately don't care about what y is. I want to know what x is. So x plus 2 is equal to negative 12. X is going to be negative 14 here. And then x plus 2 is equal to 1. X is going to be negative 1. So those are my two solutions.